Electric potential part 2. Okay, if you didn't watch the other video, I highly suggest you do, so it'll make more sense what I'm about to say. And if you want to live on the wild side and just give this one a go, by all means, have fun. Probably don't want to watch the other one anyhow. So first question is, what is the change in potential? Well, a change in potential then is measuring, what did we say? We said that an E field is KQ over R squared. And we said that potential is an E field times some R, or delta X. And the other way that we could write that is just the KQ over some delta R. Probably a better way to think of it. Let me write that out explicitly, so I'd have like KQ, and remind ourselves that we're 1 over final minus initial. What am I doing? Just like with the cliff diver, if I wanted to look at the change of potential gravitational energy between 100 to 90, I would be putting in 90 here and 100 here. Now we don't have those distances with electrostatics, so typically these are in terms of centimeters. Oops, wanted to erase that. In terms of centimeters, not meters, and that's probably the biggest warning that I can give you here is pay close attention to our distances. I know with many of our Qs we've already been, with many of our electric fields and forces, those have already been small distances. Well, it's going to stay that way, so pay attention to that. So what are the units for this? Okay, what did we say? We said let's go back to force. Okay, it would help if I have it in a PEM mode. Let's go back to force is KQ over R squared, Q1, Q2. And we know that Q1 and Q2 are in terms of coulombs, so I'd have Coulomb squared. And we pulled this K out over R squared. And so what I said in thinking of what are my units of K, my electrostatic constant, well, force still has the units of newtons. So let's see, K has units then of newtons. And I need these units to go away in order to have just a force. So it's going to be newtons per coulomb squared times meter squared. So my K still exists. So let's see what our units are for my potential. My potential then is going to be these newtons meter squared per coulomb squared. And now what am I doing? I'm going to multiply by my electric field. Do I want to do that? No, we'll just do it in terms of KQR. So I'm going to multiply that by a coulomb, and I'm dividing by 1 meter. So my potential then, let's cancel, that cancels, is going to be, whoops, I don't need two equal signs. It's going to give me something like this, that I'm going to have newtons meters per coulomb. Newtons meters, if you remember from the last video, I reminded you that that thing is joules. So what do I have? I have potential just says the amount of energy that is possessed in a field per the charge that interacts with that field. Much the same as what we talked about electric forces and electric fields. Electric force, the other way we wrote that, was that I have this electric field times a Q. And we wrote that out in terms of its units. I'm going to erase this stuff up top. Okay, that's too slow. Wrote that out in terms of its units. And we said this. We said, so an electric field K, going back to K is newtons per coulomb squared times meter squared. So I want electric field, there's my K, my Q times the charge, the coulombs for the charge creating that field, divided by the distance away. So I look at this, for my electric field, that should be an equal sign. Yeah, should be an equal sign. Sorry about that. For my electric field, then what do I have? I have the ability for some force to be experienced per charge that experiences that force. Okay, so this potential is the amount of energy that is potentially there. So it exists, nothing's experiencing it. So it's the energy stored within a field per charge that will interact with that field. So if I bring in a charge to interact with a potential difference, now I have energy. So the units for potential are going to be then just joules per coulomb. And my potential is a scalar. That was what we talked about on the other side. So how do you combine electric potential? This is because it's scalar. This is still a sum of all of the potential from all of the charges to whatever change in distance that I have to measure them. So that's going to be fun. I'm going to do some videos this weekend where we're going to apply this, and it's going to make a lot more sense on how to do it, and then you're going to be so sad that I made you do all the other work before. But we're still talking about the fields generated, but because they're scalar, we're going to sum them up, but include the charges, include the sign of the charge. Sign of charge. And the trick that we do for that is we say, okay, if I want to measure the potential at, like, say, here, relative to a charge here and a charge here, I can, like, measure the distance away, and then you say, but that's just 1r. Well, what am I doing? I'm actually going to look at, like, a potential from an infinite distance away. So one of my r's becomes 0, and I'm measuring the potential specifically in terms of those dots, but to those charges. But I am explicitly going to do some examples for you in the next coming up videos. Does electric potential increase or decrease if you move in the direction of the electric field? So remember, that has to do with the type of charge interacting. So that's a depends. That's a depends. If I have a positive charge going in the direction of an electric field, I am losing potential. If I have a negative charge moving in the direction of an electric field, I'm gaining potential. But remember, because we're taking all of this into electronics, they used to think it was all positive charges moving in the direction of an electric field. So it's going to be kind of confusing as we move on, is we're going to talk about losing potential moving in that field line. Can you have negative voltage? Sure, sure. All you're doing in lab, it's going to be like you've measured two opposite points. So instead of putting your one probe in what we see as positive to the probe what we see in the negative direction, so going from a positive into a negative, if you flip those probes on the meter itself, you would see a negative voltage, and we always just say just ignore that. That just means you got the probes in the wrong direction. But we can see from what we did before, you can have a negative potential depending on if you're gaining or losing, because I have that delta in front of there. So if something is losing potential, I'm going to end up with the negative. If something is gaining potential, I'm going to end up with the positive. So that it can be positive or negative. And then this. So let's think about this. Am I gaining or losing potential if I have this positive charge going from a positive to a negative? I am losing. Am I gaining or losing potential energy? It's the same answer. I'm losing. Because I'm going from where I don't want to be and going to where I do want to be. So my energy, my potential energy, is decreasing, as is my potential itself. Same thing here. Am I gaining or losing? Well, this is what I was saying in the other video. I am gaining potential. I'm making a negative charge go somewhere it doesn't. And I'm gaining potential energy. So moving here. Oh, that's the, I'm sorry. I panicked for a minute. I thought my drawing was bad. It's fine. So that D just is giving the direction that it's going. So positive going towards a positive. Let's see, my field line is going like this. So positive going towards positive, I am gaining. I'm going in the opposite direction of the electric field lines. So I'm gaining energy. For this one, the negative going towards a positive, I'm losing. On this below, this is similar to what you are going to see in lab. These here are the field lines. Remember, we have them defined as going into and out of. So the big thing for here, and I'll leave it for you to do, like more detail, it'll help you for lab, is to remind yourself that potential and field lines and E fields are perpendicular. So what does that mean? That means if I take my voltmeter and I make a register, I read a value here, and then I want to draw in my electric field. Well, what I want from this potential is to draw in, that is not doing what I want it to do. Go away. We're just going to deal with my bad drawing. What I want to do is draw a straight line perpendicular everywhere to my field. If you can do it. And that's what's drawn on here, is that these would be my potential lines and these would be my field lines. So everywhere to my field I have a perpendicular potential, and we can connect the dots, and in connecting the dots we actually get this real pretty view of what's going on with both our potential and our electric field. So there you have it. Now you are ready for Monday and more to come this weekend.